Hello, my name is John Sowa. I'm a professor at Seton University, and it's my pleasure to offer this webinar entitled Innovative Methods for Teaching Experimentation in Chemical Kinetics. I just wanted to give a little personal introduction for this webinar. There's me on the left in my canoe on the Passaic River in New Jersey. My teaching interests are organic chemistry, spectroscopy, and the development of teaching experiments, which is the subject of today's webinar. An outline of my presentation. I'll start off with teaching experimentation in kinetics. How to make kinetics cool. Experiments that we've developed at Seton Hall. The SN1 Solvolysis of tButyl chloride, which I will elaborate extensively on. SN2-like Solvolysis of 3-chloro-3-methyl-1-butene. SN2 Williamson ether synthesis, and a look at the acid-catalyzed nucleophilic acyl substitution of aniline. I'll talk about the logistics, a conclusion, and acknowledgements. This slide is about teaching kinetic experimentation. On the left side, I'd like to talk about chemical kinetics. It's essential characteristic of every chemical reaction. It provides information that is key to the understanding of reaction mechanism. It is essential for scale-up, that is, it's a key need in industry, especially for students who are considering careers in industry. Kinetics are covered very well in lectures, very well on paper in an academic setting. On the right column, I'd like to say that hands-on experimentation with kinetics is severely lacking in an academic setting. Why? Well, first of all, the experimentation is laborious. It requires fundamentally a synthesis step, multi-point analysis, and data processing. It's difficult to consider all of these aspects in a single experiment in a teaching environment. In fact, having been a student, I know many cases of kinetic experimentation in which the outcome is frequently disappointing. In this slide, I would like to describe my approach to the kinetic experimentation problem in academic settings. My approach, in fact, I think it's my solution, is to make kinetics cool. The way you make kinetics cool is you do teaching with instruments and software that are designed for doing kinetics. On the left, I'd like to briefly describe one instrument that I use, which is the React-IR, which is a robust FTIR. You can see by the red arrow there's a probe that you can insert directly into a reaction vessel. So this means that you can follow pretty much any reaction over time. It is not your traditional IR spectrophotometer. It does not require sodium chloride plates. So this is a really robust system, very beautiful for following the infrared changes in a chemical reaction. On the right, I'd like to describe the EasyMax, which is just a fantastic reactor. It provides wonderful temperature control of chemical reactions, and that is something that is really essential in kinetics, is to provide precise temperature control and to easily equilibrate the temperature of your reaction. One nice feature of the software that is associated with most instruments is that the software is integrated, so each instrument can talk to each itself during the course of the experiment. In an academic setting, I think we are all most familiar with use of infrared spectroscopy as a qualitative tool for characterization of organic compounds, and using sodium chloride plates, which means that we can't do anything in water. However, infrared spectroscopy doesn't have to be that way. If we have an ATR immersion probe, an attenuated total reflectance probe, infrared spectroscopy can be used as a quantitative tool and a robust tool that can be pretty much put into any type of chemical reaction. On the left-hand side, I'd like to describe what an attenuated total reflectance experiment involves. It involves an ATR crystal, which is usually a zinc selenide zinc selenide crystal. The infrared light source is passed through the crystal. As it bounces through the crystal, some of the infrared light sneaks into the reaction mixture. When that light sneaks into that reaction mixture, we call that light the evanescent wave. Of course, the reaction mixture is going to absorb some of that light. So eventually what happens when that light hits the detector, that light is going to be attenuated by the chemical compounds that are present in the reaction mixture, and changes in any chemical compound in the reaction mixture are also going to be detected in the detector. On the right side, I show a little bit more detail about the attenuated total reflectance probe. It actually consists of a very small window. It's about 1 millimeter in diameter. But don't let that fool you. The sensitivity of this detector is incredible. 10 to the minus 2 molar limit of detection I've had for relatively insensitive compounds. I use two types of probes. One is the DICOMP probe, which is a zinc selenide window, which is coated with a diamond crystal. That has a wavelength range of 1900 to 650 inverse centimeters. It's useful for most organic reactions. In fact, I find it quite useful for following organic reactions by looking at changes in the fingerprint region. However, if you want a broader wavelength range, I recommend the SciComp probe, which is a silicon window that is coated over the zinc selenide ATR crystal, and that has a detection wavelength range from 4,000 to 600 inverse centimeters. This is the first reaction that I would like to describe. It's the solvolysis of tertiary butyl chloride, and it is a classic SN1 reaction. One takes tertiary butyl chloride, dissolves it in 60% ethanol water. Over time, the tButyl chloride hydrolyzes to tertiary butyl alcohol, and it produces hydrochloric acid as a byproduct. There is some amount of ethyl tButyl ether as another product in this reaction, but by far and away, tertiary butyl alcohol is the major organic product. The reference is Duncan and Pasteau, J-Chem Ed, 1978. The challenges for doing this reaction in an academic setting is that 3 laboratory periods are required for a full kinetic analysis. The reaction is followed by doing multiple laborious titrations of hydrochloric acid byproduct. So the question I had to ask, is there a better way to teach kinetic experimentation more efficiently? Yes, there is. This reaction is ideal for infrared monitoring. In fact, you can see there's a very nice absorption of tButyl alcohol, the product of the reaction, that occurs at 1201 inverse centimeters. And also there's an excellent absorption of the tertiary butyl chloride, the reactant for this reaction, that occurs at 1156 inverse centimeters. And in fact, the way we do this reaction is we follow the disappearance of tertiary butyl chloride over time. This slide shows the traditional way to perform this reaction. You do one reaction at a time. So for example, here we're showing the disappearance of tertiary butyl chloride at 35 degrees C. We're monitoring the decrease in absorption of the 1156 inverse centimeter absorption band. And we're doing this over time. However, this slide shows a really cool way that you can do this reaction in an academic setting. Why not do all 3 reactions at once? For example, why not monitor the first reaction at 15 degrees C, then change the temperature to 25 degrees C, and continue to monitor the reaction, and then change the temperature again to 35 degrees C and continue to monitor this reaction. So in fact, this is exactly what we've done. Here is the experiment design. First, we set up the instrumentation. That takes about 30 minutes. Then we charge the reactor with 60% ethanol water, and we equilibrate the reactor to 15 degrees C. That takes about 10 minutes. After the reaction is equilibrated to 15 degrees C, we inject 1 milliliter of tertiary butyl chloride, and we measure the infrared spectrum over time for 45 minutes. Then, after 45 minutes, we do a temperature ramp to 25 degrees C. That takes about 5 minutes on the Easy Max. We measure the IR at 25 degrees C for 30 minutes. And then after that, we ramp the temperature up to 35 degrees C. That takes about 5 minutes. And we measure that reaction at that temperature for 30 minutes. Overall, the reaction time is 2 hours and 5 minutes. So with about a 30-minute setup, in 2 hours and 35 minutes, students have performed an entire series of experiments that will allow a full and complete kinetic analysis of the hydrolysis or the Solvolysis of tertiary butyl chloride. This is a demonstration of what the data looks like in terms of processing the data. It can be exported and processed in an Excel spreadsheet. The students then delete temperature ramp sections so that they focus only on the change in concentration of the tertiary butyl chloride at exactly 15 degrees C, 25 degrees C, and 35 degrees C. Now I would like to discuss the data processing that students perform. There's actually two ways that they can process the data to get rate constants out of this particular reaction. First of all, we're going to assume, or have them assume, that the reaction is first order with respect to tertiary butyl chloride. Then, there's two ways to process the data. The first way on the left is actually working directly from the rate equation and plotting the parameters presented by the rate equation. Therefore, doing this, plotting rate, which is minus d tertiary butyl chloride dt, versus the tertiary butyl chloride absorbance over the course of the reaction, the analysis gives this green line, which shows somewhat of a scattered plot, but the linear regression of that green line is shown in orange, and that slope of that linear regression line is the rate constant k. So this is actually a quick and dirty way of doing an analysis directly from the rate equation. The other way to do the analysis is certainly a more rigorous way, and that is taking the integrated rate equation, where ln of k is plotted versus time, and the slope of that line also gives the rate constant k. Notice that the slope of the rate equation on the left is similar to the slope of the rate equation, or the integrated rate equation, on the right. The students can then be asked to compare the fit of their data to other rate equations. For example, if the students are to assume a zero-order rate equation, then they plot the absorbance of tertiary butyl chloride versus time. This is done on the left side of this slide, and the students obtain a curved plot. So that shows that the data do not correlate well. On the right side, the students assume a second-order reaction, and they plot one on tertiary butyl chloride absorption versus time. They also obtain a nonlinear correlation, which is evidence that the reaction is not a second-order reaction. So, in this one experiment, students plot the integrated rate equation for a first-order reaction or the rate equation for a first-order reaction, and they obtain data that is consistent for this reaction being a first-order reaction. This table shows data generated by students for this laboratory. In the first column on the far left is the rate constants at 15 degrees C, 25 degrees C, and 35 degrees C. In the second column is the relative rate of the reaction. I thought this was interesting to put in because generally one expects that a change in temperature by about 10 degrees will double the reaction rate. For this particular reaction, changing the temperature by 10 degrees actually quadruples the reaction rate. For activation energy parameters, one plots ln of k versus 1 on t, and the slope of that line gives you gives the student the activation energy. I prefer to use for organic chemistry just the Arrhenius equation, so the slope is directly given, or directly gives the activation energy of the reaction. For more advanced settings, such as a PChem laboratory, students can use the Irene equation and calculate delta H double dagger and delta S double dagger. I'd like to make a quick comparison to the literature data that is shown in Duncan and Pastow's 1978 JChemEd article. We can see that the literature rate constant values are comparable. They are certainly the same order of magnitude. There is some difference. It looks like the reaction is faster under the system or the way that we perform the reaction. Not that much faster. One of the things that we observe for this reaction is that in our system we stir the reaction about 500 RPM. There is a significant mixing time for the tertiary butyl chloride, so the original reference actually stirs the reaction by just swirling it by hand. So maybe the difference is a difference in mass transfer. Nevertheless, the kinetic data are within reasonable agreement. This slide shows the Van Hoff plots showing the effect of temperature on the rate of reaction. Also, we compare the student-generated data versus the literature data. Both data shows nice linear correlations, reasonable agreement with each other, and from the slope of these reactions, student can obtain activation energy of this reaction. In this slide, I'd like to discuss a summary and the concept of student-generated hypothesis for this first reaction. On the left column is my discussion. The hydrolysis of tertiary butyl chloride is a rewarding reaction for learning kinetic experimentation. In this laboratory, students determine the rate constant, the order of the reaction, and the activation energy. Since a full set of data are acquired in one laboratory period, students are asked to develop an hypothesis about this reaction. In the second lab period, they are actually asked to test their hypothesis. For example, some of the hypotheses students have done is what happens when I change the concentration of tertiary butyl chloride, or what happens when I change the solvent, or what happens if I switch to a different alkyl halide. In the right column, I have outcomes. The outcome of this experiment is that extensive kinetic experimentation is obtained in 2 laboratory periods. Technology is easy enough to use that students can easily develop their own experiments. The software expedites interpretation of results, and overall, this setup helps students gain confidence in their ability to perform both known kinetic experimentation and also to come up with their own hypothesis and test those hypotheses. The next reaction that I would like to discuss is the SN2-like reaction of 3-chloro-3-methyl-1-butene. In 60% ethanol water and sodium hydroxide, this reaction produces a butynol product plus some rearrangement products. The reference is Duncan and Pasteau, J. Chem Ed, 1978. The dramatic demonstration of this reaction is that the kinetics is actually second order. How can a Solvolysis reaction of a tertiary alkyl halide be second order? Preliminary results indicate that this reaction is a nice test for using the IC Kinetic software. The next reaction that I would like to describe is the Williamson ether synthesis. In this reaction, in blue is colored benzyl bromide, which is the electrophile. In red is colored the nucleophile potassium tbutoxide. The reaction is performed in THF at room temperature, and it produces benzyl t-butyl ether, which is shown in green. The challenges in teaching are shown in the left column. Potassium tertiary butoxide is moisture sensitive and is pyrophoric. Benzyl bromide is a lacrimator. So therefore, both reagents need care when handling. Our approach to studying this reaction in the teaching laboratory is by using the React-IR, because in situ measurements minimize sampling handling. In addition, we can minimize sampling handling by purchasing solutions of potassium tbutoxide as 1.0 molar solutions in THF. And in the future, we hope to develop this experiment using sodium methoxide, which I think is a better alternative than potassium tbutoxide. This slide demonstrates the data of the Williamson ether synthesis. On the diagram on the left, we show the disappearance of benzyl bromide. On the diagram on the right, we show actually how we are detecting potassium tertiary butoxide as it shows up as an absorption at around 1930 inverse centimeters, which is quite different from the absorption of potassium tertiary butyl alcohol, which shows up around 920 inverse centimeters. Finally, I would like to discuss data processing of this type of reaction, the Williamson ether synthesis. This reaction is performed at equimolar concentrations of reagents. Therefore, it somewhat departs from a traditional method of SN2 reaction analysis, where you flood the reaction with an excess of one reagent. But because we can measure concentrations of both reagents, the benzyl bromide and the potassium tertiary butoxide, over time, we're able to process the data in a simpler way. Here the students use the rate equation for a second order reaction. That rate equation shows that the change of concentration of the benzyl bromide versus time is equal to the rate constant times the benzyl bromide absorption times the potassium tertiary butoxide absorption. To then plot the parameters of this equation, the rate or the change in concentration of the benzyl bromide versus time, versus the second part of the equation on the right side, the absorbance of benzyl bromide times the absorbance of potassium tertiary butoxide over the course of the reaction. The slope of this plot gives the rate constant K. More detailed description of designing experiments and processing data to obtain rate constants and order of reactions is provided in the IC Kinetic software. In this slide, I'd like to discuss some of the logistics behind doing the studies that I have discussed in today's webinar. In the left-hand column, the first and most important thing is scheduling needs in the academic laboratory. This particular set of experimentation requires a modular schedule. It's only suited for small classes. And of course, in this particular case, we have to do this with only chemistry majors, and it's limited to upper division courses. Now, what I mean by upper division courses is, in fact, we separate our chemistry majors from all other majors at the sophomore level. And so we have a separate section of sophomore organic chemistry students that we can develop a modular schedule for. And we have done that modular schedule. Basic instrumentation are required. One does not necessarily have to use the React IR and the EasyMax. In fact, any type of FTIR will work with a suitable probe, provided that that probe is attenuated total reflectance probe, a zinc selenide window that is stable to water and stable under basic conditions. You need to have good temperature control, so one does not necessarily have to use the EasyMax. One can perform the reaction of the Solvolysis of tertiary butyl chloride, for example, by preparing 3 temperature baths, one at 15 degrees, one at 25 degrees, and one at 35 degrees, and just allowing for equilibration every time you switch from one temperature to another temperature. And of course, one needs just an ability to do spreadsheet analysis, which is given on every computer that students have these days. In the right-hand column, I have discussion of funding and maintenance requirements. We funded our instrument through 2 ways. First, the React IR was obtained through an educational-related grant. The second was the EasyMax was obtained through departmental funding, and I had actually found that our department wasn't using their laboratory fees, so I asked my chairman if he would be willing to allow the laboratory fees to be applied toward the purchase of the EasyMax. Maintenance of the instrument is very important to consider. I would strongly consider a maintenance contract because the instruments are expensive and the maintenance contract is not that bad in terms of its expense, but it's even better because the amount of support that you obtain from METTLER TOLEDO is tremendous. Our instruments are used 24 hours a day, 7 days a week, 12 months out of the year. They have a dual teaching and research purpose, so they get used and very well used. They are quite robust, but you need some backup. Finally, I'd like to describe the modular schedule that we have developed and we're employing with our sophomore organic chemistry students. We have 12 students. I've divided the students into 5 groups and they're working through a modular schedule. I'd like you to pay attention to the yellow blocks in the schedule where we've done the Solvolysis of tertiary butyl chloride. This is a 1-week-long laboratory. The students use the React IR and the EasyMax for 2 laboratory sections. In the first laboratory section, they perform the standard Solvolysis reaction at 3 different temperatures. And in the second section, they come back and they perform a hypothesis. Notice that over a period of 6 weeks, we were able to rotate these students through the Solvolysis laboratory, and then they rotate through other experiments, including synthesis, polarimetry, theoretical, computational studies, and then we also are able to balance this particular schedule with exams and spring break and Easter holidays. So this is a schedule that seems to work out fairly well, having a modular schedule and having students gain individual expertise or group-based expertise at each particular module. In conclusion, in today's webinar, I have demonstrated one way to make kinetics cool. This way develops students' confidence in performing kinetic experimentation. It enables students to test their own hypothesis on reaction kinetics. We study one main reaction, extensively developed for the Solvolysis of tertiary butyl chloride. Although this is just a simple reaction, it's an excellent starting point for teaching kinetic experimentation. It provides an opportunity for students to use advanced instrumentation and computer technology. It's a keen way to train industrial employees on reaction kinetics and the use of this complex and enjoyable instrumentation. Advanced instrumentation and software is applicable to the study of more complex reactions, including SN2 reactions without the method of flooding and catalytic reactions. My acknowledgements. First of all, I'd like to thank you, the audience. I would also like to acknowledge the U.S. Department of Education for a FIPSI grant for the funding of the React IR, the EasyMax funding from Seton Hall University, my students at Seton Hall, my Chem 2314 organic chemistry class, one of my graduate students, Abe Cassis, METTLER TOLEDO, Paul Scholl, Simon Ray, Nilesh Shah, and Jane Riley, and my Kinetics friends, Donna Blackman and Jian Wang.